Problem goes like this. A cylindrical rod of 2 centimeter diameter and 25 centimeter long projects from a well-insulated steam vessel at 100 degrees Celsius into air at 30 degrees Celsius. The free end of the rod is insulated. Determine temperature at free end if rod is made of copper having K value 330 watt per meter Kelvin, and if it is made of steel having K value 49 watt per meter Kelvin. Please always represent thermal conductivity with a small k. This is a standard notation. Okay, so let us solve this problem. In order to solve this problem, let us first draw a schematic. So as you can see here, it is mentioned in the problem, there is a steam vessel surface. So let's say this surface represents steam vessel surface, and one fin is attached to it, and this fin is in cylindrical form. So this is the fin. Meanwhile, you draw this diagram. Now let us say temperature of this steam vessel surface is represented by Ts. It is, and the length of the cylindrical fin is capital L, and its diameter is, let's say, small d. The thermal conductivity of the material of this cylindrical rod is K. Okay. This entire arrangement is exposed to the surrounding air, having temperature T infinity and convective heat transfer coefficient H. Okay. So this is the required schematic of this problem. There is a steam vessel surface. One cylindrical rod is attached as a fin to enhance the heat transfer rate. Its length is L, K is thermal conductivity, diameter is D. Steam vessel surface temperature is, let's say, Ts, and it is exposed to the air, having temperature T infinity and convective heat transfer coefficient H. Oh. Try to draw along with me. After drawing this schematic, let us enlist all the given things. So it is given a cylindrical rod of 2 centimeter diameter and 25 centimeter long projects from a well insulated steam vessel at 100 degrees Celsius into air at 30 degrees Celsius. So this 2 centimeter is nothing but diameter of the rod, 25 centimeter is its length, 100 degrees Celsius is steam vessel surface temperature Ts, and air temperature is 30 degrees Celsius. Okay. So let us enlist. Diameter of the rod is given as 2 centimeter, that is 0.02 meter. Length is 25 centimeter, 0.25 meter. Ts is the surface temperature. It is given as 100 degrees Celsius, and T infinity is surrounding fluid temperature, given as 30 degrees Celsius. Okay. Oh, here one more parameter is given. I forgot to mention. H value of the surrounding fluid is also given in the problem itself. Okay. Apart from these values, I have been given the value of H 7 watt per meter square Kelvin. Then we have been given thermal conductivity of copper. Let's say it is represented by K1, K copper as 330. And then thermal conductivity K2, that is of steel, is given as 49. So these are the values given to me. Along with these numerical parameters, very important parameter is given here. What is that? This one. The free end of the rod is insulated. Let me enlist first. Then let explain me. Rod end is insulated. Now see, what is the importance of this rod end is insulated? You might be remembering, we have derived one governing differential equation for one-dimensional steady state heat transfer through fins. And to get the solution of that governing differential equation, to calculate the temperature along the length of the fin, we have considered different 4 cases. Case number 1, heat transfer through fin of infinitely long length, heat transfer from fin of insulated tip fin, heat transfer from fin of finite length and losing heat at the tip, and then heat transfer from fin connected to 2 different sources. Now at a time, either one case will be considered. So which case to consider? This is the question. So generally this case is mentioned in the problem itself, that you have to solve the problem considering either infinitely long fin or insulated tip fin, or losing heat at the tip, fin losing heat at the tip, or fin is connected to 2 different sources. It is clearly mentioned. And if it is not clearly mentioned, otherwise, you are free to take any condition, any case. And under that condition, it is recommended to always consider heat transfer from fin with insulated tip. That is the present case, what I am going to consider. Here it is mentioned in the problem itself. You are supposed to consider fin with insulated tip. If it is not mentioned, it is recommended you always take insulated tip fin. Otherwise, you are free to take any condition. Now, why it is recommended? The temperature distribution formula is very easy. The calculations become easy when I consider insulated tip fin boundary condition. So please remember this. Okay. After drawing the schematic, after enlisting all the given things, now let us write all the assumptions. Hemant, is this font size visible clearly? Or
Yes, sir.
okay, let me admit other students. So the assumption number one, the very first assumption will be one-dimensional steady state heat transfer. Assumption number two, there is no heat generation within the fin. Assumption number three, no thermal contact resistance. All these assumptions we have also considered during the derivation of governing differential equation. So same assumptions will be applicable for numerical as well. No thermal contact resistance between the surface and root of the fin. That is at x equal to 0. This is nothing but x equal to 0. Temperature of the fin will be equal to temperature of the surface. At this point, fin is attached to the base surface. So because of imperfect contact, thermal resistance may come into picture and temperature drop may take place. But the moment I consider there is no thermal contact resistance, temperature of the surface will be equal to temperature of the fin at the root. This is called root of the fin, and this is called as tip of the fin. So that is the consequence of that assumption. Then assumption number 4, uniform properties of fluid. What does it mean? H value is constant everywhere for the air. Assumption number 5, homogeneous and isotropic material of the fin. So 5 assumptions are sufficient. Okay. You can add, if you remember, you can add so many assumptions. But what I feel, 5 assumptions are to be written. Okay. These late joiners are creating very much problem. Okay. After enlisting all the assumptions, let us enlist what is to be found out. What you are supposed to find out actually, what the problem is saying, the free end of the rod is insulated. Determine temperature at free end if the rod is made of. So you are supposed to find out the temperature at the tip of the fin. That is at x equal to L. That is TL you are supposed to find out. So symbolically, you are supposed to find out TL, that is temperature at the tip of the fin. Then let us do the calculations.
Hello.
Hello, yes,
Sir, can you repeat the third assumption?
okay. No thermal contact resistance between the surface and root of the fin. See what happens. Let's say this is the parent surface and this is the fin. What is the concept of thermal contact resistance actually? See, when these two surfaces are joined, okay, here. Now what it is assumed, when there is a perfect contact between the two surfaces and while heat is being transferred by conduction, so when perfect contact is assumed, it is assumed there is no temperature drop. Temperature drop means if this temperature is, let's say, 50 degrees Celsius, so temperature of the surface will also be 50 degrees Celsius. Had there been no thermal contact resistance. And when there will be no thermal contact resistance, when the contact is assumed to be perfect. But what happens many times, though from the naked eye it appears the contact is perfect, but at micro level, what happens? These two surfaces, these are nothing but roughnesses, voids created due to roughnesses. So when the two surfaces are joined, such voids are formed. So area normal to heat transfer will get reduced. See, this is the perfect contact. So area will be this area. And we know heat transfer is directly proportional to a heat transfer by conduction. When there is no perfect contact, such voids will be formed. And these, because of the presence of these voids, area will get reduced, isn't it? What is the area available to me for heat conduction to take place? Only this is the area. So if area is reducing, heat transfer by conduction is also reducing at the interface, and because of this, temperature drop will take place. And because of this temperature drop, temperature of this surface and temperature of this surface, both will be different. So if I am assuming perfect contact between the steam vessel surface and the fins, so this condition will be applicable. No temperature drop, and as a result of this, temperature of the fin at the root will be equal to temperature of the steam vessel surface, isn't it? That is the consequence of assumption number 3. So very important assumption it is, because unless otherwise I know this temperature of the fin at x equal to 0, I cannot proceed further. And how would I know that temperature? By assuming temperature of the fin at the root is equal to temperature of the base surface to which it is attached. Okay. I hope you have got it. Okay, should I proceed further? Hemant?
Yes, sir. Thank you.
Now let us do our calculations. So we are supposed to calculate this TL. This TL is nothing but temperature at any distance x when I consider x equal to L. Okay. So refer the data book now. I request you please refer heat transfer data book, page number 50. On that page, some formulae are given related to heat transfer from extended surface. From those list of formulae, you please refer temperature distribution for insulated tip fin. Page number 50. In some of the data book, maybe it is on page number 52 or in 48, like that. Heading will be heat transfer from extended surfaces. I have also posted one video how to use different formulae from data book related with the field. So this formula is there actually in data book. Tx minus T infinity. Notation will be different, but this is the formula for insulated tip fin. Let me refer my data book. So formula is given like this: e to power minus mx or cos of hyperbolic m L minus x over cos of hyperbolic ml. So which formula is given, whether in this form or this form? Please check. So at any distance x, temperature distribution will be given by Tx minus T infinity over Ts minus T infinity is equal to e to power minus mx. Okay. Now, what I want, if all of you have got this formula, let us say this is equation number 1. Please refer data book. I will wait for 1 to 2 minutes. It will take some time for you to search or locate that formula. In my data book, it is given on page number 50. Hopefully everyone got the formula. Please write Y in the chat box if you could locate that formula. Okay. Yes, thank you. Now let us move further. So this is the temperature distribution at any distance x. So at the end or tip of the fin, that is at end or at the tip of the fin, x will be equal to L. So Tx will be represented by TL. So equation 1 reduces to, under such condition, TL minus T infinity over Ts minus T infinity, okay, minus ML, or in terms of hyperbolic, see what I will get, cos of hyperbolic M L minus L over cos of hyperbolic ML. This will become cos of hyperbolic 0 over cos of hyperbolic ML. You can take either this combination or this combination. Any one combination you can take. But I am explaining both. Since this is the very first numerical, I will be explaining both the combination. So considering this, it will become TL minus T infinity over TS minus T infinity e to power minus ml if you are considering this combination, or cos of hyperbolic 0 is 1. So numerator will be 1 and this will be cos of, denominator will be cos of hyperbolic ml. So please mention always, please make this practice, cos of hyperbolic m. M is also there. 0 is 1. Got it? Let's say this is equation number 2. Now, please closely observe this formula. I am interested to calculate TL. So T infinity is given, TS is given, L is known to me. I must calculate this M. Now, what is this M? If you remember, M value is also given in data book. No need to remember this formula. HP over KAC. This formula is also given in data book and its unit is per meter. So what is P? P is equal to perimeter. So for cylindrical surface, it will be pi d, and AC is cross-sectional area. For cylinder, cross-sectional area will be pi by 4 d square. So I can mention here, for cylinder, so considering P and AC formulae for cylindrical rod, I can calculate M, P pi d and K into pi by 4 d square. So from here the value of M will be 4 into H over K into D. Let's say this is equation number 3. Now, see equation number 2 and 3. How can I find out M? If I know the value of H, K, and D, and fortunately all these values are known to me. H value for air is given, diameter of the rod is given. Now there are two values of K. One is for copper, another is for steel.
Hello, sir.
Yes.
Sir, can you please repeat what have you written in equation 2?
Where?
Equation number 2, sir. Yes, sir.
Okay. You are not able to get it. It
Yes,
is
sir.
TL minus T infinity over TS minus T infinity. This is nothing but base temperature.
Yes, sir.
Did you get it?
Yes, sir.
TL minus T infinity over TS minus T infinity is equal to e to power minus ml. Okay.
Yes, sir.
Okay.
So
I
the
will wait.
cos h term I'm unable to understand.
Okay. See, you can write this TL minus T infinity over TS minus infinity in the form of hyperbolic term e to power minus ml. Now, this e to power minus ml can also be okay. This, let me explain from starting. somewhere
Sir,
I
my
have.
question is, we have there cos h m, so L minus L becomes 0. So how can we write 1? In second equation, you have given in the written in the bracket cos
Okay,
h m in the bracket 0 is equal to 1. So we don't know the value of m. So how can we equate it to 1?
wait. Uh, Let me confirm the formula from my notes. I also got confused whether it is e to power. Wait, just a minute, because I should not commit any mistake. Otherwise, it will form your wrong concepts. Okay, so please let us uh, start from the equation one itself. Okay, so please, gentlemen, correct this formula. I have mistakenly written it wrong. First, the formula for temperature distribution for insulated tip fin is Tx minus T infinity over Ts minus T infinity is equal to cos of hyperbolic ml minus x over cos of hyperbolic ml. Okay, this is the formula actually. There is no exponential term. Sorry for the mistake. Now this x can be any distance starting from x equal to 0 to x equal to L, isn't it? This x can be any distance. So I am interested at the tip of the fin. I am interested to calculate the temperature of the fin at tip of the fin, that is x equal to L. So x equal to L, I can write it as TL minus T infinity over TS minus T infinity. So this will not be there. Please correct this. Oh, sorry for the inconvenience. Okay, now I want to calculate this Tx at x equal to L. So Tx will become TL, that is temperature at the tip of the fin, TL minus T infinity over Ts minus T infinity. So I can put the value of x as L. So cos of hyperbolic m, L minus L will become 0 now. Cos of hyperbolic m, 0. Now what was your question?
Sir, cos h of 0 is 1 and we have there m as variable as well. So it should be m upon cos h ml, or is it correct?
It is correct. See, cos of hyperbolic m into 0 will become 0.
Sir, but,
Oh,
m is outside the bracket.
yes. No. It is inside. It is actually like this. Okay. I think there is a notation problem like this. Cos of hyperbolic is entire of m into L minus x. Now you got it?
Yes, sir.
Okay, sorry from my side. It is a representation problem. So m into 0 will become 0 and cos of hyperbolic 0 will be 1. Thank you. Thank you for correcting me. It is a valid argument. Okay, so cos of hyperbolic 0 is 1. So it is 1 over cos of hyperbolic ml. Now it is okay, gentlemen. Can I move further?
Yes, sir. Yes, sir.
Okay. Now I have the formula for M in terms of H and D and K, and I have the formula for TL as well. And we have two values of thermal conductivities. So I can solve this equation number 2 and 3 for case 1, considering K as 330 watt per meter Kelvin, and case 2 as considering K as 49 watt per meter Kelvin. Now engineering is over, only mathematics is left. So let us solve. Up to here it was an engineering problem. Now it remains only mathematical problem. So case 1. What is case 1? When K1 is equal to 330 watt per meter Kelvin. Correct? Now, once the value of K1 is known to me, I can write M1 for copper as 4H over K1D. So you are requested to please calculate this value. 4 into 7 over 330 into 0.02. Please check whether I have taken the correct value of small d or not. So after calculation, I will get the value of M1 as, I have this value, 2.06 per meter. Okay, after having the value of M1, now from equation 2, I can calculate TL for copper rod. TL1, let me represent it by TL suffix 1 minus, so I will directly write the value of T infinity as 30, TS as 100, and T infinity as 30, 1 over cos of hyperbolic. Value of M is 2.06 and value of L is 0.25. So after calculating this, you will get the value of TL1. Calculate this value. This cos of hyperbolic you can get directly, you can get the value of cos of hyperbolic, whatever this term will be, directly from calculator. Shift of something, shift function you have to use. So I could calculate this TL1 as 91.65 degrees Celsius. This will be your answer number 1. Please check whether you have got the same value. You can write in the chat box your answer. Did you get the same value? Okay. I hope all of you have got the values, but you don't want to share. Similarly,
Yes, sir. Same answer.
Okay. For case 2 now. Case 2, when thermal conductivity is given as, please, what is that value? 40, All of you can turn on your mic, no issue, unless otherwise it is creating any nuisance. You can turn on your mic so that every one of you can speak. "49 watt per meter Kelvin." So now I can calculate M2 as 4 into 7 over 49 into 0.02. So the M2 value for copper will be, I could get this value as 5.345 per meter. And further from equation 2, we have the equation number 2. What is that? This is the equation number 2. Now TL2 minus 30 over 100 minus 30 will be equal to 1 over cos of hyperbolic 5.345 into 0.25. So from here, TL2 comes out. Calculate. I could get this value as 64.25 degrees Celsius. This is answer number 2. Please check whether all of you have got the same answer. Now, as you can see here, when thermal conductivity of the fin material was copper, its end temperature is, tip temperature is 91.65 degrees Celsius. And when it is made up of steel, having K value 49 watt per meter Kelvin, tip temperature is 64.25 degrees Celsius. So what is the conclusion I can draw here? See, more will be the K of fin material. What will happen? More heat conduction. More heat conduction along the length of the fin. And hence more tip temperature. This is the conclusion. So this way I can solve numericals on fins. This is one variety of problem where you will be asked to calculate either temperature at the tip of the fin and heat transfer from the tip of the fin as well. Okay. Okay, one more thing I forgot to mention in the problem itself. I don't know why I have written this incomplete problem. After finding out the temperature, I can also find out. Please let me complete this problem. Also find out heat transfer in each case. I will correct this problem statement while posting the PDF in the Moodle. Okay. So you can also calculate heat transfer rate from the fin as well in both the cases. Okay. So how to calculate? If insulated tip fin is attached to this steam vessel surface, how can I calculate heat transfer rate by such fin made up of either copper or fin? So once again, refer data book. One formula is given, and that formula is K into AC into M Ts minus T infinity 10 of hyperbolic ml. Are you able to locate this formula on the same page? There is a table, temperature distribution, then fin efficiency, then heat transfer rate, like that. This formula can also be written as like this. This way also I can write this formula. Okay. So let us calculate for case 1 and case 2. Q fin for case 1 will be, K value is 330, cross sectional area is 5 by 4 into 0.02 square. M1 value for case 1 is, just now we have calculated, 2.06. Ts minus T infinity is 100 minus 30, and 10 of hyperbolic ml is nothing but 2.06 into 0.25. So heat transfer rate from the fin in case 1, that is if it is made up of copper, will be 7.084 watt. Answer number 2. Got it? Similarly, Q fin in second case, I am directly writing the formula. K value is 49. Rest of the thing will remain same. Cross sectional area will remain same. M value is 5.345 into 100 minus 30 into 10 of hyperbolic. M value is 5.345 into 0.25. So for case 2, heat transfer from fin made up of steel will be 5.02 watt. Like that. Like that, you can calculate heat transfer from the fin as well. And this conclusion will be here. Please. Sorry for this disorderness. Now this is the complete solution of this problem. I hope all of you all have got this answer.